Hello, so let's have a look at this circuit, which is a diode circuit, and we are trying to understand the behavior of this circuit. So what we see here, there is a voltage source V1 applied to the circuit. It's a DC voltage source, and it will source the current I that is going to flow through the circuit. And this is the diode circuit. A diode is connected, assuming this is the silicon diode, and we have the load that connects here. So when the current I that flows through this load, it gets a drop across this resistor, and value of this resistor is 1 kilo. So we have seen how to use ltspice, and through ltspice program we can run the .op analysis. The .op says operating point analysis or simulation. This is how what we run. So very simply, we can first apply the KVL to the circuit. This is Kirchhoff voltage law, where we see that V1, which is the voltage source V1, is connected between node V in and the ground 0. This is ground. Remember, the global ground is indicated by 0, net 0. And the diode, silicon diode, is connected between node V in and V out. That's the point. So the drop across the diode when it is forward bias, when the positive voltage is applied to the anode and the negative voltage is applied to the cathode, diode gets forward bias. Forward biased. So you see here, when it gets a forward bias, it acts as a closed switch. It acts as a closed switch. When it is reverse bias, it acts as an open switch. So this is the closed switch, and this is open switch. And we'll see here 1 second, perhaps. So when we are saying try to do the analysis of it, so let's apply the Kirchhoff voltage law, which is the no V1 voltage source V1 minus the drop across the diode VD minus the current flowing through the resistor multiplied by the value of this resistor, which is the drop of across this resistor, that equates to 0. So we know that V1, let's say it is applied as 1 volt. VD is about, let's say, 0.67 volt, which is the standard drop across the silicon diode when it is forward bias, when it acts as a closed switch, equal to I times R1, because we want to know the value of this resistor is 1000 ohm, and the value of current can be then calculated. So it is, let's say, 1 minus 0.067 is 0.33 divided by 1000. So you see the value of the current flowing through the circuit can be calculated. We have calculated, it comes about 0.33 milliampere, or right. So we can write that value 0.33 milliampere or 330 microampere approximately. So that's all. And if we want to know the voltage drop across the resistor R1, so it's simply the current multiplied by the value of a resistor. So it is R I times R1, which we know that this is 0.33 milliampere multiplied by the 1000. So it is about 0.33 volt. In another way, we can calculate the drop through this equation. You see here, VD can be given as IR1, VD equal to V1 minus IR1 actually. So it would be, let's say, you have voltage source V1, which is this 1 volt, minus IR1 is 0.33 volt right here. So it's approximately 1 minus 0.33 is about No. There is a problem here. So VD would be V minus IR1. Yes, it's simple. So what's the wrong? Where is the wrong thing? We can get it. We are correct. So V1 minus 0.33 volt, approximately 0.67 volt, right? Because we have assumed 0.67 volt is the cut-in voltage of a diode. Remember the characteristics of a diode, which is the current versus voltage. So when the applied voltage exceeds the cut-in voltage of a diode, we have this current flowing through the diode, and this cut-in voltage is about 0.6 volt, 7 volt to 7 to 0.7 volt in this range, depending on the manufacturer of the diode. So cut-in voltage of a diode is 0.617 volt to 0.7 volt. This is the range. So you have this current that flows exponentially through the diode. So after we understand the theoretical analysis of this circuit, how about we actually try to simulate the circuit? Let's design the circuit and try to simulate it. So what we do here is that we just open the ltspice program. So here, so we have actually we actually see that the ltspice circuit diagram has been created. If you right click the component, it has a DC value of 1 volt. If you right click the diode named as D1, and this is the diode model D. You can also click here, pick new diode. If you click, so you have variety of diodes, part numbers, according to part numbers, and the manufacturer names are given. So for example, the first line says it's 1N914 diode. Manufacturer is ON Semiconductor. It's a silicon diode, and we see that it's a silicon diode, and what to say, you see that it has a breakdown voltage of 75 volt. It means if the voltage across the diode is about 75 volt or more, the diode will crash, or it will have a breakdown will happen. And the average current it can withstand to flow through it is 0.2 ampere, about 200 milliamperes. So remember, the circuit under our observation that we have seen is actually the theoretical circuit that we have seen before. Its diode is handling the current about 330 microampere or 0.33 milliampere. So pretty much less than the highest possible current that can flow through this part number of a diode. And then there is a SPICE model. We'll explore in detail about when in the netlist, when you describe or write a netlist, you will have to write this model, or in the schematic, when you pick up the component from this library, any component, any diode of this list, this model will get selected. So let's try to focus on what is this model syntax. So it starts with dot model, then IN914 is the part number, then it's D for diode, and in the parentheses, the first parameter is IS, which is about equal to 2.52 nanoampere. So IS is from the semiconductor device modeling course. You can understand IS is reverse saturation current. So is when the diode is reverse biased, there is still a minute amount of current that flows through the junction. This is that current. RS is the series resistance. When there is a diode forward bias, the current flows through it, and the PN junction, diode is nothing but a PN junction. It offers the resistance of that junction. So forward resistance is about 0.56 ohm. N equal to 1, we'll see that 1.752, we'll see that number later. CJO, so it's capacitance, the junction capacitance, PN junction capacitance, about 4 picofarad. m equal to 0.4. We'll see that later. And there are so many other parameters. So for example, I average is about 200 milliampere. So what we see here. So that's the maximum current diode can withstand. This diode is by the manufacturer on semiconductor. It's a silicon diode. So similarly, you can select any diode that you want, right? And that's how we can understand that. Okay, so we actually can say that we have selected the diode, which is IN914. And now next is the register R1. Here you see that it has a value of 1K. Right click it and you see that it has no tolerance defined, nothing power rating. And the analysis that we have chosen is simply operating point. If you right click on this .op command, you see the syntax .op, where there are variety of analysis that we can do, but currently we are computing the DC operating point, and we treat the capacitances in the circuit as open circuit and inductance in the circuit as short circuit. But in this circuit under observation, we don't have any capacitances or inductances, which are externally visible in the circuit. So once that happens, you go here, click the run button, right, the left top here, or just click simulate and run, and it runs the analysis. And let's have a result here. So you see the V in was about 1 volt. That is the applied voltage right here. This is the voltage. Then V out is about 0.45 volt. So we have selected the different diodes, so it has a different breakdown voltage. So 1 volt minus 0.55 volt is the breakdown, is the cut-in voltage of a diode, not the breakdown, excuse me. The cut-in voltage or the forward voltage or the threshold voltage of a diode. So 1 volt minus 0.55 volt of this cut-in of this diode will be equal to 0.45 volt, which is appearing at net V out. You see V out equal to 0.45. And the current through the diode and the current through the resistor I of D1, I of R1 is series circuit is the same. And we computed that to about 0.33 milliampere, and it is 0.45 milliampere. That's because we have chosen a different diode here. We have chosen model of a diode, specific model of a diode. So that current, you already know how we calculated. The current would be, you can refer back to the theoretical analysis. Right here, you can see that how we have calculated that current. Now, the current supplied by the voltage source is the same because it's a series circuit, and the difference between the sign, the current is sourced by the voltage source, so that's why it has a negative sign, and the current is absorbed, current is delivered to the components and the devices in the circuit, so it has a positive sign. That's the spice convention. Okay. So once that happens, what we can do, we can right click the schematic and go to view. So spice netlist option, we can generate the spice netlist here, or we can close this and we can go to view, and we have this option here as well, spice netlist. So spice netlist, as explained to you in the previous model, is basically an interconnection of our components. It shows how these sources, voltage of current, devices, diode, BJTs, MOSFETs, etc., and the component, resistors, capacitors, they are connected to each other. So you see now the diode, it has been defined to be connected between V in and V out, and the model number has been given because we are using the specific model. And when we use a specific model, we have to incorporate this command .model DD. Okay, so it says that it's a diode model and that one. And then this .lib is automatically defined because the schematic chose the diode from the library. And then we are doing the .op analysis and all that. Let's understand what happens if we select the different diode model and try to simulate the circuit again. So right click this, click pick new diode, and let us try to see if we select IN4148. So you see now the next model has been done. Just save this and run. Click run. And now you can see we have approximately similar results. So you can go back to this session and see what were the values there. 451593 is the output voltage, and the currents are little bit different, but more or less approximately same. Let's try to do another model. For example, we are choosing the silicon diodes only. So for example, right here, they are from the on semi again. So what about we scroll down and try to get this kind of models, let's say. So you see, once you choose a model, the name of that model comes here. So right click and these values are also there. So average forward current it can withstand is about 500 milliampere or 5 ampere. That can sustain, and the breakdown voltage is about 200 volt. Remember, there is a difference between breakdown voltage and the cut-in voltage. Cut-in voltage, it means the minimum voltage the PN junction diode requires to turn it on. And breakdown voltage is the maximum voltage across the PN junction diode it can withstand. If you overcome that voltage, it will break down. So let us run this. And now you see here is the difference. So V out is now about 0.56. So it's very easy to understand what was the cut-in voltage of this diode. 1 minus 0.56, about 4.4. Right? And the current accordingly, then the current through the diode and the resistor, the current through the circuit is about 0.56 milliampere. All right, so that was all about this diode circuit analysis, operating point analysis. We'll try to see how this diode acts as a acts to the different voltage source. For example, time varying voltage source.